This is the second session of PLMW, and it's my great pleasure to introduce Niki Vazou. She is at India, and she created Liquid Haskell. So she's going to talk to us about Liquid Haskell and refinement types.
Hi, so thank you, Leo. Thank you very much for having me here. So yes, I am going to talk about refinement types, and mostly in the aspect of Liquid Haskell. I'm going to show you a demo. So how many of you know what are refinement types? Okay. I hope you don't find it boring. Okay, so for those of you who don't know, so the concept is quite simple. And it is that refinement types basically refine types with logical predicates. And this is a standard example, like the most used example of refinement types. So I am starting from an existing type. I confirm that this doesn't work, the laser. So I'm going to start with an existing type of list indexing, and I'm going to refine it with a logical predicate to encode safe indexing. And in this case, I'm going to name my argument. So I'm saying that the first argument, the list that I'm indexing, is called x's, and then my index is called I, and inside the type of the index, that is an integer, I am refining to say in-bounds indexing, right? That the index is between 0 and the length of the list, and then that is showing me safe indexing. So this is a basic concept, and I'm going to show you an example of how refinement types work. And for that, I'm going to use Liquid Haskell, that is, enter full screen, I hope. So Liquid Haskell is a refinement type checker on top of Haskell. So here I have a Haskell program, and I have my Cabal file to build the program. And all I'm doing is in the Cabal file, I'm using a plugin, and I'm saying, okay, like every time you compile your program, use the Liquid Haskell plugin to check everything. And by default, when I check things with Liquid Haskell, it has some built-in refinement types, like safe indexing. So every time I am indexing a list, Liquid Haskell will use the refinement type, and it is going to prove safe indexing. So like here, I have a test. It takes as input a list of integers, an integer I, and what I'm going to do is I am going to index x's with I click save, and I am getting refinement type error, and like we are still at the word that the error messages are simple, so they make sense. And this error says, you know, I'm expecting the index to be a positive, a natural number, and I got a value that is I, for which I know nothing. So there are many things I can do here, and the simplest one is I'm going to use a branching, and I say if your value, your index I is indeed greater than 0, then go do the indexing, else 0, as suggested. And now I like the error change, so I can come and refine it more and say I want it to be greater than 0 and I less than the length of the list, and the error got away. Nice, right? Okay, so of course I don't want it to return 0, so I can say return nothing in the other case. In the then case, I am going to return a just, and I return a maybe. So generally, the Liquid Haskell refinement types work with many Haskell concepts. Okay, what else we can do as an example? So we indexed an element from the list, and like the standard built-in that have refinement types are like safe indexing. What is the other most common error that you see in the verification world? Like most common error that exists?
Missing cases.
What?
Missing cases.
Yeah, but something very, very simpler.
Division by 0.
Yes. So division by 0. It is like if you want to give a very explanatory, like I did this to verify, it's like try division by 0. It's the simplest thing. Okay, so I get an index, I get an element from my list. It is an integer, so I can go and say, okay, 42 divided by whatever I got, and Okay, so division has the precondition that says your second argument should always be different than 0. You cannot prove that. So how can we fix this error? Okay, so I can go and give a refinement type for my arguments. And I think for me, the most essential feature of refinement types as opposed to other verification things is you can go and refine the types no matter where they exist. And this no matter where exists, it's very cool because here I have a list of integers, a collection of integers, and I can go inside here and say the collection of integers are all of them, they are different than 0. And now, I know that if I get any element from my list, it's different than 0. And so division by this element is good. And this is very good because if I didn't have the power of refinement types to go inside collections and refinement, then I have to deal with for all elements of the list. For all are dangerous for verification because you miss automation somehow. Okay, and now since we went and we put a refinement type for this list, I am going to also give the precondition so that I can get rid of this runtime check, right? So I can say that I have an input list of integers, all of them are different than 0. I'm going to name this list, and then for my index, I'm going to name it I, and I'm going to say this I is less than, greater than 0, and also I is less than the length of x's. And now I have the precondition that I need to go index, so I don't anymore need this runtime check, so I can go and remove it, and verification is good. And I can also remove the maybe. Okay. And hopefully this is good. Okay, these are the two very standard examples of refinement types. They're very good for safe indexing or whatever has to do with integers. Division by 0, they can prove it. And are there any questions? Generally, yes.
Is this all done without dependent types?
What do you mean dependent types? I cannot go past this.
Well, it seems like a lot of what you're doing can be achieved in a dependently typed language by creating types which have these restrictions.
Yeah, so for me, it is exactly.
The question for the mic.
Yes, that I can do. The question is if this is done with dependent types, and that I could do all this in a dependently typed language. So I think one of the historic answers is that refinement types are lighter way of dependent types, because I don't want to go and use the whole dependent type language, because usually it requires a lot of proof terms provided by the user. I want to have on my own programming language that I know, here Haskell, there are other, I want to be able to use concepts from dependent types. And I want to be able to have automation, to have verification, type checking automatically by external solvers that here I'm using an SMT to decide all this. But my original question is if you use the abstract idea that dependent types are types that depend on values, for me refinement types is a subset of dependent types.
Thank you very much.
There was another question? Yes.
I know, for example, Hello. For example, for a dependently typed filter function, you end up with you don't know the length of the list after you filter. How is that handled with refinement types?
So in refinement types for filter, the standard thing is you can say that the length of the result is less than or equal to the length of the input.
Oh, okay.
Yes, but the idea is even for. Let me see. Even for this simple take function, you lose the information that you took an element from your list. So refinement type checking is not complete, in the sense that you give your specification and they can be as abstract as you write them down, but then you cannot prove every property that your program has.
So just on that note, it's not possible to express that the return value is somehow reached. The return value is somehow present in the list. It's not possible to express that in refinement types. Is that right?
So you can you can say it because in Liquid Haskell we use set theory because this is decidable and we have allowed it. So you can have a post condition that says that whatever I return is an element of the yes. But again, the concept is you can express as much as you need, but the more you express, the more sophisticated properties you're going to prove, the more work you have to write down. Yeah.
Yeah, I mean, yeah, just very dumb question along those lines, but like, yeah, does Liquid Haskell does it fail gracefully? Like degrade gracefully? Like if you can't prove the thing, can you add any sort of hint, or is it like just, oh, SMT, either it will sort of satisfy or not?
So does Liquid Haskell fail gracefully? So I was very proud in this very simple example. The error messages were very graceful, on my opinion. So and then we go to the deep file. We'll go there. That we're going to prove more like type theory stuff, like very more difficult properties. And there it does not fail. Like the error messages are very bad, but like we will see a concept that lets you prove anything yourself. But you are kind of on your own.
Is there any way to express like relationships between two different objects? For example, like these two hash maps have the same keys, something like that.
You have to, yes. Let me go to the deep, because maybe you will. Yes, like there are these questions like how much you can express and. Like yes, error messages. So like so the light is the standard usage of Liquid Haskell that I suggest. Like you can use now. Like if you want to prove very simple stuff, it works. Everything will work. Error messages are good. But then we have all these questions like, can I express more? Can I prove more interesting stuff? Can I help SMT like do stuff? So like a long line of my research is addressing these things. And we developed Liquid Haskell to be able to prove like more sophisticated properties. And the standard sophisticated property is here that list is right identity. So I am expressing this here in refinement types. And concretely, I'm saying right identity is a Haskell function. Undefined proves everything. Because we are not in a type theory, we can have escape routes. And right identity is a Haskell function that takes as input a list and returns unit, like no runtime value. But what I'm doing is I am naming my input x's, and basically this is a shortcut for my result is a value that is unit that is refined with the property that I want to prove, right? That x's append to the empty list returns the empty list, and like again, like syntactic sugar for Liquid Haskell. If the value is not important, I can go and ignore it. Okay, so how do we prove this? We are going to prove it like as a mathematical proof by induction. So I have my base case that is fine unit, and then like Copilot is amazing. Fine, if it exists, I can put the right identity because I assume most of you know that like I'm going to do inductive call. Okay, and here the error messages are useless. The only thing that it's helpful, it says there is an error in line 12. So I'm going to line 12 and it says unit cannot prove this property that you want. So how do I do it? I am copying paste the property, and I am using some proof combinators that come built in from Liquid Haskell, and says this I want to prove equality of x's, where x's is my empty list. If I'm going too fast, let me know. And then again, from proof combinator library, there is a concept that says, and this finishes the proof. And this is enough to prove my base case. Just basically, this is rewriting. This is evaluation of append. So evaluation of append on empty list proves my my base case. And now I want to prove my inductive case. And again, like my proving style is copy paste. So x's, I am using my equality, and then I want to finish my proof with QED, and it says line 18. Line 18 cannot do that, and as Copilot insisted, I am going to tell it, okay, this step goes by right identity on x's. And oh no, before. So this step, this is equal because of right identity of x's. Right, so I am using some operators that are defined in proof combinators library, and I am encoding my proofs as Haskell functions. And the proof is done, and like Liquid Haskell comes with a totality check. So if I want to omit my base case, it's going to say totality error. Again, you have to search for it, but you can see a totality error. And termination error. So because my functions are total, my functions are terminating, then there is some trust that you are encoding indeed proofs by induction. Right? So that's all good, but of course automatic verification doesn't like to do this evaluation, like the easy evaluation steps. So we have developed a technique that is called PLE, proof by logical evaluation. So these are comments. If I do the the comments are interpreted by Liquid Haskell. So I activate proof by logical evaluation, which means I do not need to do the steps of evaluation. So my base case is just performed by evaluation. So I can say just unit. And this is all good. My inductive case is evaluation, inductive call evaluation. So I still need to keep my inductive call, and the rest evaluation steps are going to automatically be figured out by proof by logical evaluation. So my inductive case is just my inductive call, and I can remove the rest. And here I have, oh, go away, I don't want you. Yes, and this is a proof of right identity. Cool? Cool. And this PLE, proof by logical evaluation, I think it's very cool because it lets you like hope that proofs are figured out by logical evaluation. So for example here, I am going to prove that append is associative. What does this mean? I want to append x's, y's, and z's. On the left-hand side, I first do the y's plus z's. On the right-hand side, I'm appending x's plus y's first. And I want to prove that. And if we have done some proofs, we can assume that this is just proved by induction. And I have PLE on, so I have Copilot on. So my proof like is auto-completed. Cool? Nice, let's do one more. Yes.
Familiar with Haskell syntax. This is something that's been bugging me.
Yeah.
Is this a valid Haskell file?
Yes.
So can you, in Haskell, you can split the definition of a function in many places? Like what? Okay, I see. That's what's happening on line 32 and 33.
32 and 33, yes.
Huh?
Yes. So ASOC is like it's a case analysis. So I could say axis, and then I can say case axis. Yeah, exactly.
And the two are the same.
These are totally equivalent. Yeah. So if you're, they are equivalent though. Part of some scoping things. Yes. Why is this? Yes, these two are totally equivalent. The Haskell way of writing is splitting. Other questions? Yes.
Those special syntaxes you have for proofs, equal, 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 star, 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 QED things, do they have a semantic in terms of just Haskell, executable Haskell? I mean, can you just run the file, or do you need to eliminate all of that before having an executable file?
No, so all of these are Haskell functions that are defined and imported from proof combinators, and they are actually quite simple. So, for example, the QED is a data. That is just QED. And the question mark takes something x and y and returns x. And what else did I use? Yes, equality again. Like I'm just combining stuff. So I mean, yes, but the short answer is everything is defined in the proof combinators library that comes with Liquid Haskell. You can execute, and they are defined so that they don't really affect your runtimes, but they pass the information to the solver. So the information exists there.
Yeah, so it's a proper Haskell
It's a proper
DSL, right?
It's a proper Haskell file, and again, like I have my Cabal file, and I tell it use Liquid Haskell every time you run it.
Does it do runtime checks or not even? Like
No.
runtime checks that some things are equal, that you asserted they were equal or not?
No, no, there
Fully
is no runtime
transparent.
check because Liquid Haskell is using the Haskell compiler GHC to develop and to take all the information, but GHC does not know about Liquid Haskell. So, I mean, when we started, we said, okay, we are going to take all this information and eliminate checks from GHC, but telling GHC how to interact with Liquid Haskell, I think it's a nice project, but it's a lot of engineering. So like right now, GHC does not know about Liquid Haskell. Okay, let me do one more proof. And that's a more difficult one, distributivity of reverse and append. So I have the append, we saw it, and I am saying that if I want to reverse a function, x is appended to y's, I first need to reverse y's, then I need to reverse x's. Okay, let me try to do that. Oof. That's too smart. Okay, distributivity, I'm saying, okay, I'm going to do it by the standard proof by induction. This does not work. I have some time, I guess. Let me do the base case. It's like, how many of you know this proof? Okay, so let's do it. Okay, so if you know it, like how do we do it? Let me do it directly if you know it. Okay, so base case, do I need to use something like, is there somebody who knows, or should I just write it? There was some hands there.
Shouldn't we just evaluate?
Okay, let's evaluate. It is this proof that it... What's that?
You need a symmetric case of the proof that you had before because you're going to have plus the empty list on the right hand side.
Plus, so I need the right identity.
The right identity. Yes.
Okay. Let's see. Right identity of reverse y's, right? So this is reverse y's. And my error went in line 50, so this actually worked. And okay, so I am saying I'm going to do the inductive, like in the cons case, my inductive step, I'm going to use my my inductive call, my distributivity, and yes.
Maybe you need the associative
On.
So I guess. Oh, thank you. I guess you'll have like y's and then a singleton x and then reverse y's and then singleton x and reverse x's.
Reverse y's, reverse x's, and singleton x.
Flip the reverse x's and the singleton x.
Oh, no.
Or maybe that works.
Let me
Never
see
mind.
if the flip is working too. Okay, no. It's okay. Yeah, I knew this is a smart audience. Okay, so yeah, that's the proof. I need the two helper lemma that I used. And so as you saw, it's like, so there are two difficulties in this kind of proofs. First is that you need to know exactly the lemma that you need to use, and then it's like, what arguments, how do I call them? So Liquid Haskell comes with one more like smart tactic, and it's called like rewrite with. So rewrite with is telling me that it was off, now I'm turning it on. It's telling me to prove distributivity, go use associativity and right identity. So now I can remove the calls of right identity. And the cool thing about this, like the difficulty about this property, I can also remove that, is that you don't, like, you need to know what you're going to use, but you don't need to know exactly the arguments because like not everybody can remember. It's difficult. So this is the second tactic, and like again, in like other provers, this is on by default, but like Liquid Haskell lets you have control over it because otherwise things are getting very, very slow. Yes?
How exactly do you use these proofs in a program? Do you just like call the distributivity function in
Yes.
like in some other function where you need that property, or?
Yes, the moment that you call it, you have the refinement, it's there, and the SMT sees it, and like you can use it in your programs. So like this was all the, so the goal for me is like do the light stuff. As a programmer, you're going to need some light stuff, but at some point, like to prove the light stuff, you're going to need that append is associative. So you can prove it separately and then call it. But if you, like these are like slow to run. It's better if you don't run them.
Yeah.
So earlier when you showed us the proof for the properties of write ID, you explicitly wrote some evaluation steps that you wanted the type checker to do. But here you're relying on some properties of reverse, like the fact that reverse you pop the front element of, and then you append it at the end, and then you use this for the associative when you want to apply the associativity rule. So are these lemmas that you've already proven which are now being automatically applied here, or is this using the definition of reverse that it's automatically doing this evaluation?
No. We proved the lemma, and now we are calling the lemma that we proved before.
No, but I mean the actual property of reverse itself, like how it's defined. Is this from the definition of reverse?
No,
or?
like I have it here. I have to redefine reverse.
Oh, okay.
Because like in the first proof is like by evaluation, so I need to have the definition.
In this file?
Yeah.
Okay.
I mean, I can improve. Okay. So I have like, this is all the hidden stuff I have. But this is all. I don't cheat. So I have to prove them. And so the important thing is that I need to reflect them. Reflect means the definition goes in your logic, basically. In your Liquid Haskell has access to it. I can import things, but I need to have them reflect them in the other file. So I cannot import from Prelude. Yeah.
This could be a dumb question, but because you may have just addressed it. Also, I may just not understand. But can you nest? Once you've defined these distributivity and stuff, can you use them in your logical formulae to define refinement types?
Yeah. If I can use distributivity on my refinement.
Yeah. Once you've defined a function using refinement types, can you then use that in the logical formulae?
So I can use in the logical formula things that I have reflect.
Right. So you then have to
use,
reflect
and then this goes to if I write I can reflect only things that either are constants or use other functions that are also reflected. So it's a closure property. So I can define foo. I don't know 42. I cannot put foo here, no foo. But if I reflect foo, I'm destroying. If I write reflect foo, then I can use foo in other reflected functions, and everything that is reflected, it can go in my refinement.
I guess what I was trying to ask is, in the logical formulae, do all the functions that you use to define it have to be normal Haskell functions or that you've reflected, or can you use the functions that you define using refinement types after you've defined them to put them in your can you then reflect? You said that you can only
First I define, I reflect, and then I can put them in my logic.
Okay.
And then
Okay.
And I can reflect proofs. I can reflect many things.
Okay. Thank you.
Okay, I do have some slides. Okay, last, and then I do go in my slides.
Very quick question. I assume you have to make sure reflected functions are total?
Yes, it's totality. It's on totality and termination, and by default on in Liquid Haskell. You can turn it off if you know what you're doing. Okay, let me go in my slides. I'll try to be very quick. I have 15 minutes, right? Cool. Okay, we saw that, and this is more or less how refinement type checker works. It takes as input a program and some properties, And refinement type is a tool that is generating logical formulas from the program and the properties. And it sends the logical formula is an SMT solver that is a tool that automatically decides validity of logical formulas, and it returns true if it can prove that the program satisfies the properties. Otherwise, it returns no. And like we saw a property at the beginning, we saw the safe indexing, and at the very, very first example, we tried to prove that X is indexed by I is safe, and the information we had was nothing. So the SMT said, I cannot prove this property. It said not. And what we did then is we added a runtime check, right? So in the logic, refinement type said that I know that this condition holds, so under this condition, prove exactly the same thing. And SMT says, yes, I can prove that. So we saw that verification is case sensitive in the sense that it takes into account the conditions that it has. We saw that it's type-based, like we saw that we can refine things inside structures like lists, and this is like very, very important feature. We saw that, so no, we didn't, kind of, but it is decidable in the sense that the formulas that we put in the logic needs to be decided by the SMT solver. And okay, and the question here is yes, like it's like they are very, like these kind of formulas are enough to talk about safe indexing or division by zero. But then we saw that to talk about deeper properties like associativity, we need to do manual proofs. And these proofs are helped by these two features that we have that Liquid Haskell has, proof by logical evaluation that just unfolds the function and does step. And we also have this rewriting using SMT, we call it REST, the rewrite with. And for example, yes, it's a kind of new feature that we have. We use the rewrite with to tell it. And it has a nice theory behind that it's using like online termination to see that it's not like this rewriting process is not going to diverge. And another feature that I think is really important, it is that it is language integrated, in the sense that I am like it's called by the Haskell compiler, and it can use all the nice features that the Haskell compiler has, which means that I can use like this. I can use Copilot, I can use flight check mode, I can make it part of my development tool. It can run every time I run the developer. I can use it in the cloud testing when I release projects. And yes, so these are the main features of Liquid Haskell, and they can be used for refinement type checkers. Like they are decidable, type-based, case-sensitive, highly automated by SMT, and they are integrated on languages. And with this, we can conclude, like I can conclude, that this makes refinement types a practical alternative to other verification tools. And in the next 10 minutes, we are going to see. Three other features of refinement types, if they are expressive, if they are general, and if they are sound. And so, for expressiveness, again, if you stay in the light fragment of refinement types, it is very easy and very direct to encode things like sortedness, safe indexing. But also, like if you go in the deeper side, you can encode more interesting features. And one domain that we have, like I have worked enough, is this secure web applications. And I have to finish. Okay, maybe I can skip. Yes, I will skip this part of expressiveness, but the idea is that there is a way to encode. Yes. Okay, I skipped this part. So, what can be expressed? And the idea is, like, if you are a programmer, you can very easily use the light part of safe indexing. And if you want to do a PhD and you have a domain that you can use, you can spend a lot of time to try to encode things using like special features, maybe even like advance the tool, and you can encode domains in the refinement types. But like for the specific domains, if you want to be expressive, it is like usually it's open research problems. So let's see how general they are, refinement types. And we saw like Liquid Haskell, so they can be used definitely to verify properties in Haskell. But like this style of refinement types actually started from ML. And like when we ported refinement types from ML to Haskell, we had to address this laziness problem. So it was a very challenging part. And recently we ported them to Rust, and there the problem was like, how do you deal with memory management? And this like Liquid Rust Flux is an active project. And then there is a group of EPFL with Conchat and all that have a group that is called have a project that is called Stainless. And like, if I understood correctly, they actually want to ship refinement types in Scala. So Stainless works, but they want to have like more smooth integration with the Scala compiler. And actually, in this POPL, like tomorrow, there is a paper that is using index types for WebAssembly, but indexes is again like a very lighter form of refinement types, and they use this indexing to remove runtime checks from WebAssembly. So there are many languages that use the refinement types, and all of them need some adjusting when you develop them. So yes, you can, like if you develop a refinement type system for a language, you have to carefully think what are the features of the languages. But there are many principles that are exactly the same, and they are general. And there is a nice tutorial on how to build refinement types for your language. So there is no theory, but there is like, okay, I have this language, it has this feature. Let me explain you what steps you need so that you build it. Okay, and I am going to the last question, the last feature, if refinement types are sound. And here, like, we go back, what is the soundness of a type system? And we say that the type system is sound when it only accepts programs that cannot get stuck. And we use this syntax to encode this and say that if an expression has a type T and it evaluates to another expression E, then either E is a value or it takes a step. And this is the standard definition of saying that the type checking that is defined is sound. Okay, so what we did in the paper that will be presented on Friday is we say, okay, we have a definition of soundness, we have Liquid Haskell as a prover to do deep properties, so let's encode soundness as a Liquid Haskell refinement type, as we used refinement types to encode associativity. And like here again, we extending a little, we had to do some novelties, like we defined evaluation is a property, but like these two are quite the same. It says for every expression is 0, for every type T, if it holds the property that E0 has type T, then for every expression E, if it holds the property that E0 evaluates to E, then either, and this is very cool because this is either, Haskell's either to encode or, either E is a value or there exists another type that it steps to. And this is a refinement type, and the proof, yes. So has type, models, refinement type checker, and then evals to models evaluation. And we proved this property in Liquid Haskell in about 10K lines of code. And this is the proof. It is by induction on the evaluation, and it is like the standard property. The base case, I am calling progress. In the inductive case, I'm calling soundness on the preservation theorem. And I mean, okay, like it, so actually this is the top level proof, and it's quite cool because it uses Haskell's features to prove this property. And again, this is going to be presented on Friday. And with this one could conclude that refinement types are sound. Usually I expect some objections. let me, okay, give me 2 more minutes, I guess, to finish. But Yeah, I mean, obviously, yes, there are some problems, and one problem is that the proof happened on the model of a refinement type checker. Like, this is a theoretical problem, and an actual problem is that if you go to the repo of Liquid Haskell or like Stainless or other program verifiers, you're going to see that they have soundness bugs, where soundness bug means that the program is accepted while it violates the specification. And this is against like the soundness property. And again, the 5 soundness bugs is like a lot compared to more sound developments, like Coq, for example, that is proven to be sound. Again, like there is about 1 or less soundness bug per year. And so the reason is that Liquid Haskell implements some core that is formalized, its model is formalized, but it also has many features that are not formalized. And also, like, the implementation is huge, so we call this trusted code base, and we trust that this actually implements whatever is proved in the model, right? And so this picture is quite different in Coq, for example, or other theorem provers that are designed to be sound. So Coq has a tiny trusted code base that implements the calculus of inductive constructions. That is a theory that reduces to set theory. We know that set theory is consistent, which means that we know that calculus of inductive construction also is like sound. And the only missing part is this like trusted code base, and there is a nice project that is actually trying to prove the meta theory of this trusted code base to prove that Coq is actually very sound, and this 1 bug per year hopefully will reduce to 0. And so, like, the goal that I see in this, like the theoretical goal in this development of refinement types is that we can close the gap. We can use this like practical interface of refinement types, and we can actually have our programs checked by Coq at the end. And there is a big gap because there is a lot of features that aim for automation and practicality in refinement types. And there are ways to do that. Like, for example, last year at ICFP, there was a very nice paper. It's called Explicit Refinement Types that could serve as a tool to close this gap. Or then we can develop a CIC-like theory that can actually be proven consistent of refinement types. And this goal would lead to a tool that is more practical from the user side and also like sound from the foundational side. But for now, I'm going to have a crush in the soundness part, and I'm going to thank you for your attention.
We have time for a couple more questions.
There was a question there that I stopped. Yes. Okay.
And Niki, wonderful stuff. Are you familiar with this, very old-fashioned prover called ACL2?
Yes.
If you are familiar with it, could you comment on how the fundamentals of your prover differ from ACL2?
It doesn't have this property that you can refine elements inside the structures, right?
I actually know very little.
Yes, I think this is one of the key, it's like refinement types combined in theirs from ACL2, from runtime checks, from many things. But I think one difference is this, that the refinements go in the types, and the types can be inside containers, inside functions, inside everything, and then using the typing rules, it's more easy to deconstruct what you are actually sending to the solver.
I was curious about, so you showed that undefined can inhabit any refinement. So I was curious about how that factors into your soundness result. Do you have to make some statements about how there's no undefined in your programs, or?
Yes. In my theoretic soundness result, yes, undefined is not in the in a calculus that you're going to prove sound, you cannot have undefined because it's actually undefined is implemented in Haskell as undefined is equal to undefined, so this will not pass my termination checker.
Okay. But it is still usable in Liquid Haskell. So this is an exception to the termination checking, or
So no, because termination checker runs per module. Undefined is defined in Prelude, and we haven't a module that defines undefined, it will fail the termination checker. But when you import things from Prelude, Prelude doesn't run undefined. Do I answer the question?
Yes. Okay.
I was curious how refinement types interact with optimization. For example, we had to rewrite reverse to be inefficient. Do they work with an optimized version of reverse, or do we have to have the naive version?
It depends on what properties you want to prove. If you have an optimized version of reverse and you want to prove theorems about it, I think it will be more difficult to prove theorems. But there is actually a proof there is a paper, Theorem Proving for All, that proves that the reverse and its optimized version are actually equivalent. So yes.
Okay, so if you have some optimized version, you typically have to rewrite it in a less optimized version and prove equivalence?
Yes.
Okay.
I think we're out of time. It's already 45, so let's take the next
you.
of the question after and thank Niki.